Okay. Uh, Thank you for completing the evaluation. If you didn't do it, I sent you an announcement, so you have until, I think, next week, Monday or so. Please take some time to complete that. Let's review one of the core concepts that we have been dealing with the past couple of lectures, changing from time domain to phasor domain. So if you remember, in this part of the course, we are dealing with sinusoidal functions, for example, v and I. Now, we call these signals time domain signals, right? So these signals are in time domain because they are functions of time. Now, how about these guys? What do we call these? Phasor domain. Also, if you remember, we can call them frequency domain. And the reason for that is that in this domain, all the components, resistors, capacitors, and inductors, are replaced by the impedance, which is frequency dependent. That's why we call them to be in frequency domain. Now, I'm going to define a new quantity. So, before doing that, I want you to remind you of something. Do you remember the RMS or effective value? And if you do, what is its relationship with the amplitude of the sinusoidal function? Yeah. So if you remember, VRMS or V effective is equal to Vm, which is the amplitude of the signal, divided by √2, right? Now let's define a new phasor form based on the RMS value. So this is my new phasor. Instead of using bar, I'm using tilde. So V tilde is defined as Vm over √2 with the same angle. Obviously, instead of writing Vm over √2, I can write Vrms with the angle theta v. The same goes for current. So Im divided by √2 with the angle theta I, it's equal to Irms with the angle theta I. So what is the only difference between V tilde and V bar? Yeah, one of them is using the amplitude of the sinusoidal function. The other one is using the RMS value of the sinusoidal function. The phases are the same, okay? What do we call these? These are still phasors, but we call them RMS phasors. Okay? Now, you remember this equation from the previous lecture. This is the equation that we had for instantaneous power, right? That's the general equation. That's the most general equation that I have. Okay, do you remember what was the label for the real part of this instantaneous power? Sorry, not the real part. The time-independent part of that. The average power, right? The time-independent part, the part that is DC, not a function of time, it's called the average power, as you can see it here. Okay, this is something that we learned previous lecture. Now, instead of writing 1/2 The only thing that I've done here is that I have broken 1/2 into the product of 1 over root 2 and 1 over root 2. I think you agree with that, right? So this is my final equation that I have right now. Okay, the last one. Just instead of 1/2, I have written 1 over root 2 times 1 over root 2. Now I want you to tell me this. What do you call this? V effective or V RMS, right? And what do you call this? I RMS. So you should agree with this equation. P average is equal to V RMS, I RMS, cosine theta V minus theta I. So very similar to the equation that we had, but instead of using 1/2 and the amplitudes, I'm dropping the 1/2 and I'm using RMS values, okay? So not much difference. But can someone tell me if P average is a good quantity, is a good criteria to analyze our circuit or no? No, I mean generally, not based on the specific circuit. Generally, P average or the average power, is it a good quantity to talk about how much power is being handled by our circuit or no? Why not? If no, why not? What is its drawback? It doesn't show? What else? No, it can be applied to AC circuit as well. That's the whole idea. The average power should be independent, and that's the whole point. But there is something that this guy cannot evaluate. On the contrary, that's the only element that it can evaluate, right? So let me ask you this question, maybe help with the previous one. What is the average power of inductor and capacitor? 0. It doesn't give you any information about the capacitors and inductors in the circuit. It is only focusing on resistors, okay? That's why it's not a very good, I mean, I'm not saying that it doesn't have any value. Yeah, it's very important in terms of understanding how much of power we're going to actually use for example, for our loads. But it's not a complete parameter, okay? It lacks something. That's why we define a new power term. It's called complex power, okay? And based on the definition of complex power, which you can see, and that is a mathematical concept, complex power, it's defined as V tilde times I tilde conjugate. V tilde and I tilde, you know them already. We defined them today. Let's substitute the expression that we have for V tilde and I tilde, and let's see where we go with that. So I have S bar, which is my complex power, equaled. What is the expression that I have for V tilde? Do you agree with this? V RMS with the angle theta V, right? That is the expression for V tilde. What is the expression for I tilde? I RMS theta I. And it should be conjugated. Okay. It's equal to. Now, V RMS is there. theta v, let's just repeat that. Now what happens to a complex number in polar form if it is conjugated?
It's like a negative angle.
Yeah, the only thing that changes is the angle. It becomes negative theta I. How do you multiply two complex numbers in polar form? You multiply the magnitudes and you add the angles. Okay, I have a new equation for complex power. I'm going to write here complex power in polar form. How can I change this polar form into rectangular form? Bonus point. If someone tells me how to change this from polar form into rectangular form. Yes? Tell me what to write.
You put VRMS times IRMS cosine of theta V minus theta I.
Then
Minus
plus. Why minus?
plus VRMS IRMS sine theta V minus I theta. Wait, theta I.
You got your bonus point, but you're missing something.
The 1 hour.
No. Very important part of it. See, you change it from polar to rectangular. Rectangular has a real part and imaginary part. So what you're missing is this guy, right? Do you agree with that? And just to make sure that you're following how we got from the red box to the next equation, what is that very, very famous equation called? Euler's equation, okay? This is from Euler's equation, okay? So this is complex power in rectangular form. Is the real part of this guy familiar to you? That's the average power. From now on, I may just use P. Instead of P average, I may just use P. Okay, you might think that, okay, that should be confusing. But the only other P that I have in my calculations is the instantaneous power. You either have instantaneous power or average power. How to recognize them? How can we tell which one is being asked in the question?
If it's asking around about a time.
If it is asking at a specific instant of time, then it is instantaneous. Okay? Now, what is the units of P average? Watts. So let me write it here that this is average power. And the units is watts. Now, what do we call this guy? This is something new. So the imaginary part of the complex power is called, or is shown by the letter Q, and it's called reactive power. And can you tell me why we need this reactive power sometimes in our calculation? No. Because it represents inductors and capacitors, okay? The average power alone cannot have any contribution from inductors and capacitors. That's why we bring the reactive power. Now, what is the units of that? The units is called VAR. Okay, what is? Video assistant referee, huh? It's voltage, volt amps reactive. So the reactive part is just some description. And volt amp, do you agree that volt amp is the same as watt? So why do we write it as volt amps, not watts? For the same reason we write radian per second. You know that radian per second unit-wise is exactly the same as 1 per second. But we write it as radian per second for what? To let the reader or the audience know that we are talking about angular frequency, okay? Or for example, what else do we have that is similar to this? I didn't talk about this, but yeah, we have some other quantity that has a unit like this. I'm going to talk about it when we get to that. Okay, so that is it. And this guy, which is complex power, S bar, has the units of VA, which is volt amps. So you have 3 power units: volt amps, VA, W watt, and VAR or VAR, volt amp reactive. Okay, based on what I've written here, do you agree with this? Let me see if I can make some room. Equally important equation for complex power, and that is complex power in rectangular form. Okay? Now, the real part of complex power, which is called P average or P, is just what our appliances use and what you pay for, okay? When your utility bill comes, you pay for P, okay? What is Q? Q, as we talked about, is a temporary supply and absorption of energy by inductive and capacitive part of the circuit, okay? We're going to talk more about this concept in the next lecture, but right now just we need to understand that the complex power is divided into 2 parts: the real power or the average power. Real power and average power are can be used interchangeably. And the Q, which is the reactive power. Now, let's bring this equation, the complex power in polar form again here. This is complex power in polar form, right? And you know that V effective, the same as VRMS. We have two new names again. The magnitude of this parameter, the magnitude V effective times I effective, is called apparent power with the units of volt amps. And the angle is called power angle. Okay, so two new definitions. I can write it like that. So complex power is equal to apparent power with the angle theta s, which is the power angle. I can write it here. Theta s is defined as theta v minus theta I and is equal to power angle. And don't worry, all of these equations are on the formula sheet. Okay, in order to understand this better, let's consider the 2D complex plane. And you know that complex power is a complex number, so I can show it on the 2D plane. S bar is a complex number. Okay, can you tell me what is the purple line? No, it's not. What is the magnitude? Okay, let's just focus on the purple one. What is the purple line? Do you see the purple line or no? Sorry, yeah. Now I get it. The line looks purple from here. Okay, I'm talking about this. This is purple on my screen. That's the average power or real power, the real part of the point, right? So that is P, the average power. What is this guy? Reactive power. Q. What is this guy? Which is called? Apparent power. Okay? Remember, very important question. What is the difference between complex power and apparent power? Apparent power is just the magnitude of complex power. Complex power is a complex number, so it has both the magnitude and the angle. But apparent power is just the magnitude. That's why it helps. See, the length is called the apparent power, but the point, the coordinate, the point, the complex number on the plane is called complex power. What do you call this angle? Power angle, okay? Theta s or theta v minus theta I. Any question? So this is a summary of what's important for this part, for this lecture, and for this series of lectures, actually. You have all of these equations on your formula sheet, so you don't have to worry about memorizing them. But as we will see in solving an example, you will see that it is very important to know which one, to know where to use which one, okay? So we're going to practice that. You can refer to this summary later. Now, let's derive some alternative relationships for complex power. Before doing that, let's assume that I'm focusing on a piece of circuit like that, And this is V tilde, which is the RMS phasor of voltage, and this is I tilde, which is the RMS phasor of current. And this is the impedance Z. Now, based on the piece of circuit that I've drawn, that I just drew, do you agree with this equation? The underlined one. What is that called? What is that equation called? Ohm's law applied to impedance, right? So Ohm's law. Okay? And the first equation is just the definition of complex power, okay? So I'm guessing you're okay with both of the equations, right? The first one is the definition of complex power. The second one is just Ohm's law, right? Let's combine them and see what happens. So I'm going to write V tilde itself. Instead of I tilde, can I write V tilde over Z based on Ohm's law? And then conjugate it. When you conjugate a fraction, both numerator and denominator will be conjugated. So it will be V tilde conjugate divided by Z conjugate. And it's equal to. What is V tilde conjugate?
It's just B squared, the magnitude of it.
The magnitude squared, okay? So the magnitude squared. Is there any other name for V tilde magnitude? Someone said it. VRMS. See? V tilde magnitude is just VRMS. Okay? Very important equation. Now let's see. On the formula sheet, it's here. This is the equation, right? V tilde magnitude squared over Z conjugate. That's the equation. On the formula sheet, you don't see the bar above S. Instead, it is written in bold. That's the notation some textbooks use. Okay, if you look at S, it's in bold. But there is no difference. I mean, S and S bar are the same thing. Okay. With the same, in the same way, we can find another equation based on current, the second red box that you see. Okay? Both of these equations are very useful. Both of them are given to you in the formula sheet. Okay? Now I have a couple of questions. First of all, someone tell me, why are these equations useful? Because we already had complex power equations here. We had the rectangular form, we had the polar form. Why are those two new equations useful?
They let you solve for complex power with just VR.
Perfect. In order to calculate the complex power over an impedance, okay, it's very important. You should have the impedance. You only need either voltage or current, not both of them. As you know, I told you previous lecture, whenever you see power, the word power, immediately think of finding voltage and current, unless There are some conditions provided for you, so you can only you may only find one of them. Okay, either voltage or current. So this is the case. So the first important note about these two equations is that they allow you to find the complex power based on having just voltage or current. The second important thing about this is, here is the scenario, here is the situation that happens for you. After doing a couple of examples on this concept, you get probably a little too confident on the concept. And then, even though these are given to you on the formula sheet, you don't refer to that. And you've memorized it because of solving several problems. What happens? You forget that one of the equation has z conjugate, the other one is just z. That's a very common mistake. Are you following what I'm saying? See, the one with the voltage, the one where z is at the denominator, is appearing with a conjugate, but the one with the current doesn't have any conjugate. Okay? So you need to remember that. Okay, now that I have these two alternative equations, let's apply them to different loads, for example, resistor, capacitor, inductor, and see what happens there. Okay. For a purely resistive load, what does it mean, purely resistive? It means that it's only resistor. So R is some positive value, and X, what was the name of X? Reactance, okay? So reactance is 0 because it's purely resistive. Let's rewrite the equation for S, or S bar. So I should write Vrms squared divided by. What is the impedance of a resistor R? R. Let's use the second equation. Again, what's the impedance of R? Is R. I Rms squared. So this is my S. And you know that S bar is always equal to P plus JQ. Now, based on this equation, can you tell me what is P and what is Q? Q is 0. P is R I Rms squared. What can you tell me about the sign of P? Positive always, right? What does it mean? It means that resistors always absorb average power or real power, right? Resistors absorb average or real power. Let's do it for an inductor. So S bar is equal to Vrms squared divided by, what is the impedance of an inductor? J omega L, right? Is that a correct equation to use or no? It should be conjugated, right? It's equal to Vrms squared divided by negative J omega L. I can bring negative J up, becomes positive J. If I use the second equation, the one which works with current, it will give you positive J omega L IRMS squared, right? Now, I want you to tell me what is P? What is P for an inductor? 0, because there isn't any real part. What is Q?
Q equals the J, the RMS, or omega L.
Small mistake. Q is equal to?
Just the RMS.
No J. J is not part of the Q. Remember, we have P plus JQ, okay? So Q is equal to VRMS squared over omega L or omega L IRMS squared. What can you tell me about the sign of Q? Always positive. So what does it mean? Inductors fill in the blank. Absorb, because it's positive. Yes, provided that the polarity and the direction that you've defined is like that, okay? If you define it the opposite way, everything is going to be opposite, right? Okay, let's do it for capacitor. S bar is equal to VRMS squared divided by, what's the impedance of a capacitor? Negative J over omega C. It should be conjugated, right? So it becomes the negative J becomes J and omega C. Then I can bring up the J and make it negative J. Negative J omega C VRMS squared. How about IRMS is equal to negative J divided by omega C IRMS squared. Okay, so tell me, what is P? 0. What is Q? Why did you forget the negative part? The negative sign. Okay, that's a very important part. The only thing that you should drop is J. J is not part of the Q, but the negative sign is. So Q is equal to negative omega C VRMS squared or negative 1 over omega C IRMS squared. Okay? And what's the sign of Q? Negative. So tell me what to write. Capacitors supply reactive power. Any problem? Let's do an example. Okay, this is the circuit. Average power, first part is asking average power absorbed by ZA. Then it is asking apparent power absorbed by ZB, reactive power absorbed by ZC, and complex power supplied by VS. So let's start with ZA, part A. So ZA. Again, remember, whenever you hear or see the word power, what do you immediately think of? Voltage and current. You should have voltage and current to calculate power. So let's go for the element ZA. Now, do we have its voltage or current? We don't have either of them, right? We don't have them. So we should find them. How do you find them? Which one do you want to go for? Voltage or current? How? And yeah, that's a good idea. So you want to do voltage division between ZA and the combination of ZB and ZC, right? That's one way to do it. Perfect. No problem. What's the other method that you can use? Someone mentioned it. Oh, absolutely not. Don't go for them. I mean, well, in this case, you're safe because you will get one equation, one unknown. Yeah, that's fine. You can do it. But I would try to avoid that, okay? As long as you can. The other way is to find ZEQ, okay? After you find the equivalent impedance, if you divide the voltage by equivalent impedance, what will it give you? The current passing through here. Let's call this guy I tilde A. Okay? So first, I'm going to calculate ZEQ, which is equal to ZC in parallel with ZB plus ZA, which is equal to ZC times ZB divided by ZC plus ZB plus ZA. Give me the value.
Got 12.123 plus 4.747 times.
Okay, can you please read that again?
12.923 plus 1.747 J.
0 point or 1 point?
1.747.
Someone else can confirm that? Okay. What's the units? Ohms. Does it matter which representation I'm using here? Why not? Because what I'm going to do with this, next step, I'm going to divide the voltage by this, right? So it doesn't matter whatever form that is. I'm not going to use that directly. Okay, after I've calculated ZQ, IA is equal to what? Is that correct or no? Is that correct or no? Sorry?
Looks like it could be correct.
Which one? Oh, the final answer?
The I.
There's something wrong with this equation. What is that? Someone is talking. Is it William? No? No, that is not that one.
Wait, which question?
This is Ohm's law.
Oh, which equation did you say is messed up?
Yeah, which one's messed up?
The I. Oh, there's no, your.
This guy.
voltage is just direct.
Yes. See, we want to work with RMS values based on all the equations that we have. But the voltage that is given to you as the voltage source is not RMS value. It's just a standard value. How can you tell? Well, you might think that, okay, this is a bar, not a tilde. But that's not exactly very promising because the notation might change or might be different in different textbooks. Usually, in order to let the reader know that we are talking about RMS value, we write the unit in RMS too. So we write it as 120 VRMS, which means the voltage that is given to you is RMS, not direct or not a standard. So I would have written it like this if I want it to be RMS, but since it's not, then it is just a voltage. So what should I write instead of this? Vs, or I can write like this. I can write Vs tilde is equal to Vs bar divided by root 2, which is equal to 120 divided by root 2. What is the angle? 0. And then I will write the unit as VRMS. That is my RMS phasor. And then I can write I tilde A is equal to V tilde S divided by ZEQ, which is 120 divided by root 2 with the angle 0 divided by 12.923 plus J 1.747. Give me the value of that.
Do you want polar or do you want
You should tell me.
polar?
Okay, give me polar.
Okay. 6.507 angle negative 7.699.
Can you tell me what's the units?
Yeah.
Amps RMS. Yeah. Because it is the RMS value. Okay, now, first of all, okay, so I have the current. Go to the equation sheet and tell me which equation I should use to calculate whatever the question is asking. The question is asking for average power. Which equation should I use? The very first one is a trig identity.
We're trying to find average power for which
We're trying to find the average power, right? What do we have? We have the impedance ZA and we have the current passing through that. So tell me which equation I would choose. Should I go for these guys or no? The very bottom left. This guy? Is this a good option? Yeah, because it's giving you average power. But do we have enough information right now to find this? What don't we have? We don't have V effective. It's the voltage across the element. We don't have it, okay? So can we find it? Yes, we can, based on what law? Ohm's law. Just apply Ohm's law with the current and the impedance and you will find the voltage. Am I clear? This is the first method and I'm not going to use that, but it's perfectly fine. But I want you to understand that you can do this. So you have the current, you have the impedance, multiply them, it will give you the voltage. The magnitude of the complex number that you get as voltage is going to be your V effective. Then you have V effective, I effective, cosine theta V minus theta I. It's going to give you your average power. That's perfectly fine. But I'm going to do this. I have only current and impedance. What if I use this equation? Is it going to give me average power? No. But if I use this equation, what quantity I will find? Complex power. Is it very, very easy to find average power from complex power or no? Just write it in rectangular form and it will be the real part. This is my suggestion. For most of the power questions, I would personally prefer to calculate the complex power. I'm going to do it for the first one and you'll see why. Okay? So, first of all, the good advantage of that is that you don't need to calculate voltage. You only have current and impedance, and that's enough. So, let me write the equation. Complex power is equal to Z, let's add a subscript of A, ZA, IA, I'm going to write it like that, I RMS A, no, it doesn't need a bar here, or I can write it as ZA dot, instead of I RMS A, I can write I tilde A magnitude, right? These are equivalent. Okay, what is ZA? ZA is given to you, is 6 plus J3 ohms multiplied by, what is, this is the part that I'm going to start. Preston, what is IA tilde magnitude? Or the I RMS A? It's right on the screen. You just need to focus on the name of the variable that I'm interested in. I'm interested in the RMS value of the current that's passing through A, passing through ZA. Can you tell me what's the current passing through ZA? Remember, the magnitude of IA tilde is the RMS value of the current. Now, I'm going to ask the question that Hannah asked me. She asked me which form I prefer for IA tilde. Can you answer that now? Which form do I prefer, rectangular or polar? And why? Why? Because you immediately get the RMS value. But if it is in rectangular, you have to change it, okay? Sorry? Finally, at the final step, okay? Not now, okay? Okay, so this is what I have as the answer to this. I'm going to write both of the forms, 254 plus J127 or 284 26 degrees. And both of these are in volt amps. Together are in volt amps. Now I'm going to ask next person. Please tell me, what is the name of 284? It might be a little difficult, but it's a very good practice for you. And please don't, anyone else, don't say it. No. This is not voltage, this is power. So everything in these four, I'm going to ask you these four, okay? All of them are power related. So what is 284?
Power in joules.
Power is not in joules. What kind of a power is that? That's the important part. You have a dozen terms for power by now. Do you want to use the P word?
The P word.
Do you know what the P word is?
It's about the average.
Pass. Next.
What about pass?
What? No. Only 284, what is that called? Yes. What is that called? Apparent power. The magnitude of complex power is called apparent power. In volt amps. Do you want me to go back to you? No? Are you sure?
I was never going to get that.
How about now that he sort of got you? Can you tell me what is 254? No? Okay, Chaz.
That would be the 280.
What is it?
The real part, right?
Which is called average power. And the units is in watts. Who's next? Hannah. What is 127? It's nothing average. Do you remember S was equal to P plus J?
Is it relative power?
Reactive, not relative. Reactive power. Yeah. Q or reactive power. And finally, look, what is the name of this guy? The easiest one. Power angle. Let me ask you a more difficult question. What's the units? Degrees. Yeah. Okay, so do you see the point of calculating complex power? You immediately have access to all 4 of them, okay? So for me, this is the preferred method. Whatever is asking, I don't care. I go for complex power and immediately. And you know why is it useful? Because most of the time in the question that you get for the 3rd exam, one circuit is sometimes related to more than one question. Get the point? Several questions, and you have access to more than one piece of information. But, yeah.
Will there be a problem on test where it's like, it'll be like a problem, like, if, like, if you did solve for complex power, we would have solutions like 3 problems, or?
It might be. Okay, let's go for next part, which is ZB. What do I do with ZB? Next is Luini. Breda. Don't forget on the apparent term first, okay? Forget it. Just see the power. When do you see power, you need to calculate voltage and current, or only one of them. Now, let's focus on the element ZB. Is there any way you can find either its voltage or its current?
Voltage is the current going through it.
Pass.
As
Ross. Jonathan.
You do a current division?
Current division. You have IA, right? So you can find the current that is being divided into ZB and ZC and find the current IB. Do you agree with that? Let's do current division. I should write ZC over ZB plus ZC. Okay? And this is what I have, 3.8 with the angle 23.7 degrees amps RMS. William, what's next?
Square that and multiply it by ZB.
Pretty much exactly the same as what we did for the first part, right? So SB is equal to ZB dot IRMSB squared, or instead of IRMS, I can just write IB tilde magnitude square. And what's the, I mean, you have everything, right? ZB is 9 minus J8. Next, what is IB tilde magnitude? It's right on the screen, screaming at you.
3.8.
3.8, thank you. Calculate the value and you'll get next, let me ask Cage. I'm gonna write both the polar and the rectangular form, but based on the question that part 2 is asking, tell me which one I prefer. Why? because the magnitude will directly give you apparent power, right? Let's go back to that side again. I'm going to ask you the same question, okay? You can pass, but please don't. What's the name of 174? Perfect. That's what this question is asking, okay? So apparent power. Next. What is the name of 129.96? Let's see. Luini, what is the name of 129.96? Xavier, what is the name of 129.96? What is the label for that?
Label?
Yeah, what do you call that?
I have no idea.
Samuel.
Where it says 129.96.
That's the real part of complex power. What do you call it? Average power. What do you call negative this guy? Q. What do you call this angle? Power angle. Okay? CB. How do you find the power, the reactive power absorbed by ZC? Who's next? Seth. Current division is perfectly fine, but is there easier way to find IC? IA minus IB will give you IC, okay? So it's an easier. IC is equal to IA minus IB, and everything else is the same. So this is what I have, 3.815 with the angle negative 39 degrees, ARMS, and then SZC or SC is equal to ZC dot IC tilde magnitude squared, which is equal to 21 degrees, 3.815 squared. Okay, next. Yes, John.
21 degrees?
21 degrees, yes. And Aaron, which form do I prefer?
Looking for reactive, so you want rectangular.
Yes. And which part is Q?
The complex J.
Q is equal to 63 VAR. And finally, the voltage source. but it's asking for supplied. Okay? Calculation of supplied power by Vs, is it consistent with the direction and polarity of Vs and Ia? Can I use them? Yes. So it's already consistent. Can I use the equation that I've been using for the first three part? Why not?
Because there's a conflict, you have to make the cosine.
No, why can't I use the same equation that I was using for the first three parts? It's not an impedance. What's the impedance of a voltage source? You don't know it, so you can't use that. So we have to go for the general equation that we have, right? Can you tell me which one? V dot, are you talking about V dot I conjugate? That's one way. What else?
Could you do like a, the V squared over R by Z conjugate?
Sorry, again?
V squared over magnitude of V, or VRMS squared over Z conjugate?
What is Z?
Is EQ.
That's good. Let's talk about it later. Okay, let's focus on these equations for now. This one, right? Do you see that? Let's see if you have everything. I want you to tell me what the values are. Preston, you ready? No? Can you tell me what is V effective for the voltage source? Easy questions.
You asking?
No, Preston.
So what is the V effective of the voltage source?
Yeah. V RMS or V effective of the voltage source. Next. Next.
120.
Next. Next.
120 over square root.
Perfect. 120 over root 2. So we have VRMS. What is IRMS? Next, Chaz. Magnitude of which current? IA, which is 6.5. Okay? So next, Hannah, what is theta V? V is the voltage source. Okay? What is theta for that? 0. Right? Look, what is theta I? Okay, just replace all of that and you're good to go, right? So remember, this is S bar. I'm going to write Vs here so you know that the complex power is calculated for the voltage source. And it's equal to VRMS, IRMS with the angle theta V minus theta I. So you have everything. The first one is 120 over root 2. The second one is, I don't remember, what was it? 6.5. And the angle 0 degree minus negative 7.7. And the answer is equal to 552 with the angle 7.7 degrees, and that is volt amp. Okay. Now let's get back to what Cameron was saying. Is there any other way to find the complex power supplied by the voltage source? Yes?
Could you add all the previously found power to
Based on what law in physics?
power? I think it's power equals power. It might be.
Conservation of energy, right? Whatever complex powers the source is providing should be absorbed by other elements. So just add other complex powers that you calculated for the first three part, and you'll get this, okay? That's it. That's very equivalent to what you were referring, Cameron. You wanted to deal with the equivalent impedance, okay? That's very close to what we were doing. So I'm going to write it here, or SVS, but I'm going to add this subscript supplied is equal to SA absorbed, SB absorbed, plus SC absorbed. Yes?
So why can't we have the main current coming out of the source, right? Did we find that? Can we just multiply that by the DRMS, just like IV, and you get the same thing?
You don't get the angle.
So we know, we'll just plug in 0. Oh, it only works because it's 0 for the direct current source.
Yeah.
Okay.
But I mean, what you're saying is not wrong, but you have to be careful to add the angle to the number to make it complex, and the angle is the voltage angle minus the current angle, right? Any question?